Today we're going to be learning about how to graph a rational expression, a rational function, using a couple different techniques we've been working with. Before we get started, we're going to review how to graph these two linear equations. If you remember from way back when, we kind of said that if you have a line equation, y is equal to 4, it's almost like a horizontal line drawn at the point y is equal to 4. So I'm going to go up 1, 2, 3, 4, draw a point, and then draw that horizontal line through that point. And then kind of conversely here, x is equal to some value, so there's no slope, there's an undefined slope rather. That's kind of a vertical line through that point. X is equal to -1. So I'm going to go left 1 and draw a vertical line through that point. So remember guys, a rational expression is a ratio of two polynomials. We kind of talked about these as rational expressions or algebraic fractions. So a couple examples of each rational expression here. We could just have a simple one, 1 over x, which we're going to be working with a ton today. Or we could add or subtract from that x, or even have like a quadratic on the denominator. So we're going to start by graphing this parent function y is equal to 1 over x. And we're going to do this by evaluating 1 over x at 5 different values. So I've got a table, an xy table set up for us. And every time that we evaluate, 1 over x, we're going to input a value for x and get out a y value, and then we're going to graph that point. Okay, so let's start with the x value -2. So we're going to do -2, -1, 0, 1, and 2. We're going to get out 5 y values. So let's evaluate f of -2 first. F of -2 is 1 over -2, so it's just -1/2. So now on my graph, I'm going to go graph that. I'm going to graph -2, left 2, and then down 1/2, which is about right there. Next up, I'm going to evaluate f of -1. So f of -1 is 1 over -1, which is just -1. And then just like I did with f of -2, I'm going to graph that point. So I'm going to go left 1, down 1. There's my new point. Next up, I'm going to graph f of 0. And this one's kind of tricky because it's like 1 over 0, which we can't really divide anything into 0 pieces. So this is actually undefined. So we'll talk about that a little bit more in a moment, but the only thing you need to know for now is that at this point, 0 comma undefined, that nowhere where x is 0, so at any place where x is 0, nowhere exists. So we can't really have a point at the origin. So let's keep going. Let's try to see kind of the formation of this graph. So I'm going to graph f of 1, which is 1 over 1, or just 1. And then finally f of 2, which is 1 over 2, or just 1/2. Okay, so let's go graph these 2 points, 1 comma 1, and then 2 comma 1/2. Okay, and what we're going to notice as we take smaller and smaller values, or bigger and bigger values rather, for x, or more negative values for x, what we're going to notice is that the points on this curve, they get really close to this axis, this x-axis. Okay, and also if we took fractions in between 0 and 1, so if we took like 1/2 for example, these points get really close but don't actually touch this y-axis. Okay, and this curve is going to kind of look like this. So it's a curve that goes through all of these points. It gets really close but doesn't actually touch each one of these axes. And you can kind of see this happening for both the negative versions and the positive versions of this curve. So if we go back up to that previous slide, we can actually draw on some asymptotes. So I'm going to draw my asymptotes in a different color, and asymptotes are imaginary lines. So there's something that the curve doesn't touch. So we're going to draw them kind of as like dotted or slashed line, dashed lines. So I'm going to draw those over the x and y axis, okay? And this is for the graph of y is equal to 1 over x. So this brings us to this idea of an asymptote. So an asymptote is defined as a line, a vertical or horizontal line that a graph or a curve approaches, but it doesn't intersect or cross over. So you can kind of see on this horizontal asymptote, it's kind of like the one we just did, right? Where that all those points got like really close, but didn't actually cross over that x-axis. And same with that y-axis. All those points got really close, but didn't actually cross over or touch that y-axis, okay? We're not gonna talk about any oblique asymptotes, in this course, but definitely something to look forward to. So once again, your graph should never cross that asymptote. So the asymptote or the dashed line, it's kind of like a boundary line, like in sports, like in soccer. It's something you can't cross over. So it kind of helps us graph these curves, just because it gives us like a boundary, something to aim for as we're getting infinitely close to it. So, once again, as we graph these rational functions, for this one, we kind of already did it, so we know that the points are at, 1, 1, and 2, 1 half, and -1, -1, and -2, -1 half. And we kind of had asymptotes at this x-axis and asymptotes at this y-axis. So I'm going to draw those dashed lines that are imaginary, they're not actually real. And then our curves get really close to that, asymptote. They don't actually cross over, okay? So then the question for this one is, can you write a line equation to describe these two asymptotes? So I'm going to highlight this vertical one first. So can we write, a line equation? Remember, vertical lines can kind of be described as x is equal to the value that the x-coordinate goes through. So the x-coordinate goes through 0. So this vertical asymptote is x is equal to 0. So then if I want to do the same thing for this, horizontal asymptote, or the one that goes left and right, I could, right? I could say that y is equal to 0. So this would be my horizontal asymptote. And as you graph all of these rational functions, it's important not only that you graph, 4 or more points, but also that you're graphing these imaginary asymptotes. And you're also hopefully labeling these asymptotes as well. So the last one we're going to do today is kind of an exploration that's going to lead us into the topic for tomorrow. So we have a rational expression, y is equal to 1 over x plus 4. So I'm going to get my xy grid out. I'm going to graph label a bunch of points in the table, and I'm going to use the points -2, -1, 0, 1, and 2, just like I did before, but I'm going to evaluate them in this new function now. Okay, so I'm going to evaluate f of -2 in 1 over -2 plus 4. I think that's going to give me a 1 over 2. Okay, so -2 is just going to be a positive 1 half. Okay, next I'm going to do -1, so f of -1 is equal to 1 over -1 plus 4, which is equal to 1 over 3. Next up, 0, so I'm going to do f of 0 next. So I've got 1 over 0 plus 4, which is 1/4. So you can kind of see these fractions getting smaller and smaller as we're going from left to right. Next up, I've got f of 1 is equal to 1 over 1 plus 4, which is 1/5. Okay, and then hopefully we kind of see the pattern. F of 2 is going to be 1 over 2 plus 4, which is 1/6. Okay, so I'm going to go graph all of these points. I'm going to do this in blue. So I'm going to graph -2 comma 1 half, -2 comma 1 half. I've got -2 or -1 comma 1/3, 0 comma 1/4, and then 1 comma 1/5, and then 2 comma 1/6. You can kind of see these points getting smaller and smaller, getting really close to that x-axis. The issue is these 5 points that we graph, they don't really give us the whole piece of the puzzle. They don't give us enough information to graph this whole thing. So I'm going to evaluate at a couple different points. I'm going to evaluate at, f of -4. I'm also going to evaluate at f of -5. And I'm also going to evaluate at f of -6. And hopefully this gives me enough information to graph the rest of this. So f of -4 is equal to, 1 over -4 plus 4, which is 1 over 0, which is undefined. Okay, so I found my asymptote. It's at f of -4. So I'm going to go to -4, and maybe in a different color even. I'm going to graph my vertical asymptote. So that's super important that you know where that vertical asymptote is. Another way to think about it is, hey, what number on the denominator is going to make this denominator 0? In this case, it was -4. So my asymptote was x is equal to -4. Next up, let's evaluate f of -5. So I'm going to have 1 over -5 plus 4, which is 1 over -1, which is just -1. So I'm going to graph -5 comma -1. Okay. And then finally, I'm going to graph f of -6. So I've got 1 over -6 plus 4, which is 1 over -2, which is -1/2. Okay, so I'm going to also graph that point, -6 comma -1/2. Okay, and we can kind of see, these curves form. We can kind of see this curve on the positive side of things get really close to that asymptote, and then kind of same on the kind of lower left half of this graph. I can kind of see those points getting really close to these asymptotes. The last thing I need to do, I need to draw my horizontal asymptote, which I did not do, which kind of goes through that y-axis, so that didn't change at all. So you can kind of see, y is equal to x plus 4, or y is equal to 1 over x plus 4, versus y is equal to 1 over x. You can kind of see that the vertical asymptote, it almost got like shifted by adding 4 on the denominator, shifted over 4 units. We'll talk about that more tomorrow. All right, today we're going to continue our conversation with graphing, rationals, but we're going to actually transform them. So today we're going to be moving them up, left, right, and down. So just a reminder, these, rational functions, the graph for 1 over x, it does have, a horizontal and a vertical asymptote. We kind of talked about yesterday, the properties of those horizontal and vertical asymptotes. They're always going to have, a dotted line on our graph, and also they're going to be described as x is equal to, some number for vertical, and y is equal to some number for horizontal. And we talked about oblique, how we're just not really going to cover those in this unit, or in this course rather. So on these 4 graphs, we're going to take a look and try to describe each horizontal and vertical asymptote. So I'm going to start with this one on the top left, okay? And I'm going to notice that it has 2 asymptotes, two lines, two imaginary lines that our curve gets infinitely close to. So first I'm going to start with this vertical blue one. So that's at x is equal to -2. So I'm going to write a line equation for that. Remember, line equations for vertical lines are x is equal to some number. So the vertical asymptote is x is equal to -2. Next up, I'm going to identify this horizontal asymptote, which I don't think moved at all. It's still just at that origin, so it's still at y is equal to 0. Okay, so that would be our horizontal asymptote for this rational function. For this next one, it looks like our vertical asymptote, it didn't move at all, so it's still at that x is equal to 0 mark, still at that origin. But our horizontal asymptote did move, so it's at y is equal to -1. For the last 2 here, you're going to notice that both of my asymptotes moved this time. So my vertical asymptote, it looks like it moved, right 4. So it moved right 1, 2, 3, 4 units. So the vertical asymptote is going to be described as x is equal to 4. And my horizontal asymptote moved up, right? It moved up 1, 2, 3 units. So it's going to be, y is equal to 3, okay? So notice on this one, we had a double transformation. We had to move right, and we also had to move up, okay? And then finally, in this last one, you can kind of see how we moved to the left. So my vertical asymptote went from x is equal to 0, it moved all the way to x is equal to -1. Okay, and my horizontal asymptote, it also moved down. So it's going to be y is equal to -2. Okay, kind of see that shift down 1, 2. So obviously, graphically, it's pretty easy to see transformations take place. It's pretty easy to see the shifts right and up from that parent function. But from an equation, it's a little more challenging. But I think really all you need to do is remember HIVO. Remember, HIVO stands for horizontal is happening inside and vertical is happening outside. And when I say inside, like horizontal transformation is happening inside. What I mean is inside of parentheses. And I know this, rational function doesn't technically have a parentheses written, but it's kind of got a hidden one because the denominator of a fraction, it does group everything on the bottom, with a parentheses. So this, subtraction of 1, it is a horizontal shift right by 1 unit. Remember, inside the parentheses is always kind of opposite of the sign. So if we're subtracting 1, we're really kind of adding 1. We're adding 1 to all of the x coordinates. So we're shifting right by 1 unit. So in the equation, like anything on the denominator, it is a horizontal, transformation. In this case, we're shifting because we're adding or subtracting, okay? So you can kind of see that connection between that horizontal inside meaning inside or on the denominator of our fraction, okay? Vertically, though, is a little different. Vertically happens kind of beyond the fraction, outside the parentheses, high-vo, vertical, outside, okay? So in this case, our vertical transformation is a vertical shift up by 2 units. So we would have to add 2 to all our y coordinates. So in this next one, it's kind of the same thing, right? All we have to do is recognize, these operations that are happening to the parent function y is equal to 1 over x. Are they happening, underneath the fraction sign, or are they happening, outside that fraction sign, or outside the parentheses, inside or outside? In this case, the thing that's happening kind of inside my parentheses, or underneath my fraction, is that addition of 3. So this is really, a horizontal shift left by 3 units. So we would have to subtract 3 from the x coordinates. Okay. So then the other transformation taking place is this subtraction of 2, and that subtraction of 2 is happening outside of our parentheses again. So we can kind of say that this is a, vertical shift down 2 units. Remember, vertical transformation is kind of just business as usual. So plus is up and minus is down. So hopefully we see the difference between, addition and subtraction, whether it happens inside or outside. It's going to depend if it moves my function here up, down, left, or right. So that kind of brings us to, I just want to summarize, all the different transformations we've talked about so far with rationals, a vertical or a horizontal, translation or shift, and kind of what the different, addition or subtractions mean, for each transformation. So remember, vertical is business as usual. So an addition, it moves our function up. It's an upward transformation, upward translation. Okay, and subtraction moves it down. So vertical is kind of business as usual. And horizontal is the opposite of the sign. So like addition, typically you might think it moves something right, but actually addition moves our function left, and subtraction moves our function right. Okay, so this would be a really good chart for you to remember. Just kind of the only really trick to it is that, horizontal, kind of opposite way of the sign. Which brings us to, one of the, tougher problems on today's notes, where we have to graph this rational function. So I'm going to go through this process just like I did, in semester 1 with transformations. So I'm going to start with my parent function. So I'm going to write a table, x comma y, of the parent function y is equal to 1 over x. This is not the function y is equal to 1 over x minus 1 plus 2. I'm writing the table for 1 over x. Okay, so I'm going to use the points -2, -1, 0, 1, and 2. Okay, if I evaluate x at -2, I get y at -1/2. I get -1, I get undefined, I get 1, and I get 1/2. Okay, and I can even, on my graph, I can kind of graph, I don't know, maybe in yellow, just like a ghost function of what this looks like, just so I can see the actual transformation taking place. So I kind of just maybe do like a dotted yellow line or something to represent, my parent function. So my parent function was done in yellow. okay? And I didn't even draw the asymptotes on there, guys. I'm really drawing this parent function just so we can eventually see the shifts happening, okay? So next up, I'm gonna label my transformation. So just like we did in a couple slides ago, I'm gonna say that this is a vertical shift up 2 units, okay? And I try to color code mine. And I'm gonna say this is a horizontal shift right 1 unit, okay? So let's start with the vertical. So my vertical shift up 2 units, this is happening to my y coordinates. So to all of these y coordinates, I gotta add 2. So I've got -1/2 plus 2, which gives me, so -1/2 plus 2, I think that gives me 1.5, or 1 1/2, or 3/2. Then I've got negative, so out with the old and with the new. I've got -1 plus 2, which is a +1, okay? Undefined plus 2 is still undefined. I just got to know that I'm shifting this up 2, so I'm going to have a horizontal asymptote at y is equal to 2 now, okay? But it's still technically undefined. And then 1 plus 2 is 3, and then 1/2 plus 2 is 2.5, okay? So I'm taking out my old y coordinates, and now these are my brand new shifted up y coordinates. I got to do the same thing with my x coordinates here. I got to shift them all right 1 unit, which means I add 1. Don't get tripped up on that. I know it's a subtraction of 1 in the function, but remember it's the opposite of whatever's happening. So I've got -2 plus 1, which is a +1, or -1 rather. -1 plus 1, which is a 0. 1 plus 1, which is a 1. And remember that vertical asymptote is going to be at that x is equal to 1 mark, because we shifted it right 1. And then I've got, 1 plus 1, which is 2, and then 2 plus 1, which is 3. So out with the old, in with the new. So I've got a brand new set of x comma y coordinates, okay? I'm going to start by graphing -1 comma 1.5, okay? -1 comma 1.5. We'll do this graph in black here. So -1 comma 1.5 will be about right there, okay? I graph that one first. Next, I'm going to graph 0, comma 1. Go right and left 0, up 1. Okay. Next, I'm going to graph my horizontal and vertical asymptotes. X is equal to 1 and y is equal to 2. So I'm going to go graph x is equal to 1. Remember, that's a dotted or a dashed line. Okay. And then y is equal to 2. We shifted that up 2 units, so it's going to be about right there. Okay. And I'm going to keep going. So I've got, so I graphed my horizontal and vertical asymptotes, x is equal to 1, y is equal to 2. Next, I'm going to graph 2 comma 3 and 3 comma 2.5. So 2 comma 3 next, right 2, up 3. And then 3 comma 2.5 is going to be about right there. So I can kind of see this curve forming. It looks exactly like that parent function, but we just moved it up and right. Moved it up and right. So a couple of things to note. One, I definitely want to see on your work, I want to see these points. I want to see these points that we found from our table, and I definitely want to see these asymptotes. Those asymptotes are kind of like our boundary lines in basketball or soccer, okay? They're super important for us to graph it accurately, but also to make sure we get all the points on the test. You need those, and they need to be dashed lines. All right, so for this next one, guys, it's kind of the same thing. I'm going to start with, graphing my parent function table, okay? So I'm going to graph -2 comma -1/2, -1 comma -1, 0 comma undefined, 1 comma 1, and then 2 comma 1/2. And remember, this table is for the parent function y is equal to 1 over x. This is not for my transform function, which I'm about to do. So next up, I'm going to label my transformations. So this is a vertical shift down 2. So I've got to subtract 2 from all these y coordinates. And then I've got a, horizontal shift left 3. Remember, it's the opposite sign of whatever's taking place. Okay, so I've got to subtract 3 from all these x coordinates. So let's apply these to our table. So I've got -1/2 minus 2, which is -2.5. -1 minus 2, which is -3. Undefined minus 2, which, remember, that's just going to shift my... So it's still going to be undefined technically, but it's going to shift my asymptote down, 2 units. I've got 1 minus 2, which is -1, and then 1/2 minus 2 is a -1.5. Okay, so I'm out with the old, in with the new on my y coordinates. Let's do the same for our x's. We have -3 minus 2, which is -5, negative 1 minus 3, which is negative 4, 0 minus 3, which is negative 3. Remember, that's going to shift my vertical asymptote to x is equal to negative 3. Negative 3 plus 1 is negative 2. And then finally, the negative 3 plus 2 is a negative 1. Okay, so out with the old, in with the new. So I've got all my points. I'm going to start by graphing kind of my asymptotes, guys. I'm going to graph my y is equal to negative 2 and x is equal to negative 3. Okay, so let's go do that real quick. So y is equal to negative 2. I'm going to go down 2, graph that horizontal line at y is equal to negative 2. And then I'm also going to graph my, vertical asymptote at x is equal to negative 3. So down, up and down, x is equal to negative 3. My vertical asymptote. And then you'll start to notice that if you graph those asymptotes and there's only shifts, you really can kind of surmise where those points are. There's always going to be a perfect point kind of 1, 1 unit away on the top right and the top left, okay? But of course, we've got those perfect points on our table. So we've got negative 4, negative 3 and negative 2, negative 1, which we just graphed. Next up, I'm going to graph the negative 5, negative 2.5. So I'm going to go left 5, down negative 2.5. You can kind of see your curve forming from there. And then finally, that last point that we have to graph is negative 1, negative 1.5, which is about right there. And then I'm going to kind of see your curve forming. Just remember, your curve cannot touch that asymptote. It just gets infinitely close to it. All right, so this brings us to kind of our last type of problem, which actually is a transformation of our graph 1 over x, but it's not a shift at all. I would not describe this as a shift. This is actually what's called a reflection. Right, so we're multiplying everything by negative 1. So you might remember from last semester how if you multiply something and you put a negative 1 in front of the equation, it's a vertical reflection. If you put it inside the parentheses, it's a horizontal reflection. So the question is this negative in front of my rational a vertical or horizontal reflection? To be honest, it's both. They both work. I'll show you. So let's graph our parent function, y is equal to 1 over x. So I'm going to graph x comma y, or table x comma y, negative 2 comma negative 1 half, negative 1 comma negative 1, 0 comma undefined, 1 comma 1, and 2 comma 1 half. Okay, and we're going to treat this for this one like it's a horizontal reflection. So we're going to be multiplying all of these x coordinates by negative 1. Okay, and then we're going to graph it. So I'm going to multiply all of these x coordinates by negative 1. So this is going to be negative 1, times negative 2, which is a positive 2. Negative 1 times negative 1 is a positive 1. 0, we're going to have an asymptote at x equals 0 still. 1 times negative 1, which is negative 1. And then negative 1 times 2 is negative 2. Okay, so out with the old, in with the new. You'll kind of see the flip happening already. So let's go graph this thing. So I've got, asymptotes at x is equal to 0 and y is equal to 0. So I'm going to graph those first. Graph my asymptotes. Okay. And then I'm going to go graph those points. So I'm going to graph 2 comma negative 1 half. So right 2 down 1 half. I'm going to graph 1 comma negative 1, which is right here. And then negative 1 comma positive 1. And then negative 2 comma 1 half. So you can kind of see your curve forming. Getting really close to those asymptotes, but not touching them. Kind of see your curve forming, okay, in red there. All right. So that was if this negative in front was a horizontal reflection. Okay. So now the thought project I want to do here is why couldn't this be treated as a vertical reflection? Okay, because it is technically outside the parentheses. And the answer is it can. Okay, so let me get my table down. And I want to show you guys, why it's kind of both. Okay, so let's treat this as a, vertical reflection. So let's say, hey, this is a vertical reflection, which means it's going to take place. It's going to happen to all my y coordinates. So I'm going to multiply all these y coordinates by this negative 1. So this becomes, positive 1 half. This becomes positive 1. This is still undefined. This is negative 1, and this is negative 1 half. So you can kind of see that vertical reflection taking place already. But let's go graph this thing. So let's go graph our asymptotes at x is equal to 0 and y is equal to 0. You'll notice they're right on top of the other asymptotes we just drew. Okay. So a negative 2 comma 1/2, let's go graph that point. Oh, it's already a point on my curve. -1, comma 1, oh, already a point on my curve, so you can kind of see that curve forming, okay? And then I've got 1, comma -1 and 2, comma -1/2. So you can kind of see how my graph for a vertical, if I were to treat this as a vertical reflection, is the same exact graph as a horizontal reflection. Okay, it's still got asymptotes at x is equal to 0 and y is equal to 0. It still has those perfect points, so we ended up getting the same exact graph, whether we treated it as a horizontal or a vertical reflection. Why is that? Well, let's kind of go back in time and let's talk about just fractions real quick. So if we have a -1 over x, that is the same thing as -1 over x, or a vertical reflection. And it's also the same thing as a 1 over -x, which is a horizontal reflection. So all of these, fractions, they're all the same thing. So, really you can have only one type of, reflection when it comes to rational functions.